Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Hello, I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Our guest today is Dr. Mario Livio, Senior Astrophysicist at the Space Telescope Science Institute in Baltimore, Maryland, which operates the Hubble telescope. Mario Livio was raised in Israel and received his PhD in theoretical astrophysics at Tel Aviv University there. He was professor of physics at the Technion Israel Institute of Technology until he joined the Space Telescope Science Institute in Baltimore. Dr. Livio is distinguished for his research in several areas of astrophysics. He's published hundreds of professional papers, and he's a fellow of the American Association of Advancement of Science. But he is more familiar to the general public for his outstanding science books, for which he's received both the Peano Prize and the International Pythagoras Prize. He's a very popular lecturer as well, and has appeared also on major networks, on TEDx, on 60 Minutes, and many other programs. Dr. Livio is recently on book tour with his new brilliant Blunders book, and he has kindly agreed to talk to us today about several things, including his new book. First, a couple of important contributions in his own research. Second, his books for the general public, not just the one. And third, one of his great personal passions, which is art, and you will find the reference to this in all of his books. It's a very special honor to welcome Dr. Livio and to hear from a truly cultivated scientist who's deeply committed to encouraging public interest and understanding of the scientific and mathematical concepts that shape modern civilization. Welcome, Dr. Livio.
My pleasure.
And we will start in, as I said, we're going to cover a lot of ground if we possibly can. Bear with us. We'd like to start with your work in particular. You've covered a number of things in astrophysics. Is there anything that you especially like, have been pleased with? Well,
I like everything I do, clearly, but you know, maybe I like very much work I did on these stellar explosions known as Type 1a supernovae, because these were the best tools that led us to the discovery that the expansion of our universe is not slowing down. In fact, it's speeding up. So that's one part of my work I like very much. And another part of the work I like very much is I did work also on extrasolar planets. These are planets around other stars. Theoretical work on that. You know, that's on the path that maybe one day will lead us to discovering life elsewhere in the universe.
Right. And very quickly with the Type 1a, before you leave that, are these used as what are called candles?
Yes, they are used as standard candles. Yes. Yeah. So a standard candle, the idea is very simple. Is if you have a candle and you know how much light it emits, by seeing how much you receive from it, you can tell how distant this candle is. And Type 1a supernovae have this thing that they are very, very bright, first of all, so you can see them halfway across the universe, but also they are nearly all have the same brightness, and the small differences that exist are well calibrated. So they are very good distance indicators. You know, we see them, we can tell how distant they are, and that tells us, you know, how the universe looked many years ago, billions of years ago. And by comparing the expansion of the universe then and now, we can tell what the universe is doing.
I see, because that's such a huge, difficult thing. The distance problem is a different thing. So one other thing that you have done, and I remembered in Accelerating Universe, one of the books we'll talk about, but it's come up in other areas, is something called the anthropic principle. And this may not be familiar to everybody. It is an issue. Your paper, at least one of them, was cited as one of the best on this, that resolved a problem that Fred Hoyle introduced about carbon, how carbon is produced, particular carbon. Can you give us a background?
Yeah, so the anthropic principle actually raises the blood pressure of many physicists. The idea is that there are these things called selection effects. Let me maybe explain what that is. If you have a fisherman and he or she, they catch fish, but the holes in their nets are, let's say, 10 inches, they might conclude that all fish are bigger than 10 inches because the smaller fish would just not be caught. Well, in the same way, so you need to take care of that. Now, in the same way, the universe that we see is observed by us. So the universe that we observe must somehow be consistent with the fact that we are here as observers, that our universe allowed for galaxies to form, planets to form, life to emerge, and all that, and so on. And in recent years, there have been some suggestions that there isn't just one universe. Our universe is a one pocket universe, but that there could be a huge ensemble of universes. And of course, we would find ourselves in one member of this ensemble that allowed for us to actually emerge within it. This is the general idea. I originally was also very much against this, this concept, I must say. But like I say, recent ideas in astrophysics, in particular this idea of inflation, that our universe has undergone some big expansion at the very beginning, and ideas coming from string theory, our best attempt to unify all the forces of nature, suggests that there may be a reality to this ensemble of universes, and indeed I did some work on that.
The thing that I was thinking about on that, if I can just pursue that for 1 second, was that Fred Hoyle, who comes up in Brilliant Blunders, made a big to-do about the particular carbon that we need for life. But he said, no, carbon is really special, that you have to produce this, the stars produce this, but it's so extraordinary. And that was one of the things that you had replied to that said...
Yeah, Fred Hoyle, I talk about his blunder, but I also talk about the fact that he was a genius, and he really was.
Absolutely.
And at one point he did this phenomenal work where he basically said, look, you have to produce carbon in the universe. And it turned out that to produce carbon, the carbon nucleus needed to have a particular energy level that would just be right for carbon to be produced. And he predicted that such a level should exist. And then experiments showed that actually that level indeed exists. Now, one of the questions that have been raised was, to what extent that level needs to be precisely where it is, or can you shift it a little bit? And I did some work which showed that you could shift it a little bit and carbon would still have been produced.
All right. And that really was a big contribution. That solves a lot of problems. It doesn't solve the problem whether, well, some people think we're the only...
I would not call it such a huge contribution, but it was, on my part, on Hoyle's contribution, it was a huge contribution.
Yes. Stephen Weinberg thought it was a big contribution. So you got a lot of praise.
I'm flattered.
Yes, okay. And now, in Brilliant Blunders, you have made a very strong case that basically we have to make errors. This is the very nature of investigation. It's part of the science process. But you get the impression today, with so much retraction of funding, at least in this country, that scientists are much compromised as to what they can do, that maybe the pressure is very great to conform with whatever's going on, and that is actually the case. What do you think? Is there space to make errors?
I think that first of all, I do think that blunders are part and parcel of the scientific process, but I want to make it very clear. I mean, I'm not advocating to do sloppy science or careless science. I'm for doing thoughtful and very careful science. But the point I'm trying to make is that sometimes to make a breakthrough, you need to think outside the box.
Right.
And to think outside the box means that you think in unconventional ways. And that means that you take some calculated risks, but where there is a potential for very high reward as well. So I'm trying to advocate that all creative processes should have some element of that. Now, it is true that it is difficult to advocate this to a funding agency, because funding agencies, you know, they normally like to think that, okay, you can tell exactly what you're going to do, and so on. Now, this leads to incremental science, which is very, very important, but sometimes you may miss on the breakthroughs. So we need to devise processes, and it can be done, which allows for a certain element of risk-taking, again, not to make sloppy things, but a certain element of risk-taking. And we used to do this with the Hubble Space Telescope for a while, where we allocated 10% of the available time on the telescope for what were deemed risky proposals. These were proposals that, you know, it wasn't certain whether they can achieve the goals that have been declared, but that if they would have achieved, then they could produce a very, very important result. So you can design, you know, your funding process in such a way that it would also allow for a certain level of risk-taking, again, careful and thoughtful risk-taking. I mean, I want to emphasize, my book is called Brilliant Blunders, not sloppy blunders.
No, it shines through. There's not a word in your book or in anything that you've written that would endorse casualness by any means. If anything, it underscores the tremendously hard work, and that despite the tremendously hard work and your level of genius, there will still be these difficulties. But the issue here is more that scientists feel afraid of getting off of any kind of a track that's laid down for them. Is there any difference between countries in your experience, having been in
I don't think there is a huge difference among countries. I think that maybe some of the private research companies are perhaps a little bit more open to this type of thing. For example, you know, I think in biomedical research, for example, I think they are very aware that many of the discoveries have been made serendipitously.
Absolutely.
Serendipity plays a very important role. I mean, you know, more than half, I don't know, maybe it's up to even 90% of the discoveries, are, you know, they try to develop something for blood pressure, it turns out to work for depression, you know, and things like that, and so on. So the process should allow for that, for these type of things.
Right. So, well, there is still a problem wherever you are in terms of trying to fund science in the right way to give it as much air as possible. Now I'd like to switch to you as the ambassador from science to the public with your tremendous writing and speaking skills. One of the things that you've done, which some might say was risky, was to bring mathematical concepts that are not easy to the general public. And there's always implied, look, you can understand this. Maybe not 100%, but the general public can get it. What drives you in doing this?
Well, you know, I'm a theoretical astrophysicist. I always liked mathematics. I mean, my undergraduate, was in mathematics and physics. And mathematics is what I do for, you know, my living. So I liked mathematics. Some of my more mathematical books had to do with somewhat simpler concepts, like, you know, the golden ratio, which is just one number which appears in many things. Probably the most challenging was when I wrote a book, The Equation That Couldn't Be Solved, which tried to explain in layperson's terms group theory, which, you know, before I wrote that book, there really wasn't a good popular book about group theory, in my opinion. And there was a reason for that. It's not easy to write about group theory. It's a very abstract concept. And I think many people still find that book quite challenging. But, you know, that's the language of symmetry. And symmetry is all around us, from, you know, the way our face looks, from the way the laws of physics behave, and so on. So I felt that one needed to write a book about that. And since then, I'm actually happy to say more books have been written, and so I think that, you know, people are starting more to open up to that.
Yes. Is it, first of all, I'd like to say that to mention you are a theoretical astrophysicist.
Yes, yes.
A lot of people at the theoretical end really don't love communicating with the general public. So you've done a tremendous job of this, but it's also a great public service because this is not easy stuff. But the other is it difficult to write this? How does your mind work when you were trying to do this to bring group theory?
It's very difficult. I mean, look,
more than a technical paper.
Sure, to explain things in mathematics, sometimes all I need, not to the public, but to professionals, sometimes all I need is to write down one equation, and they immediately get what I want to say. When I try to write for the public, I cannot write down that equation because that would mean that nobody would read the book. So I need to give the essence of that equation in words and also in terms that people can actually relate to. So I spend a lot of effort thinking about how to explain those rather complex concepts, not just topics, you know, in writing. So it's tough.
It's got to be a lot of work. Are publishers challenging in this respect? Well, you know, it's almost a joke here that thou shalt not use equations. So you're going to talk about the universe and you're going to talk about physics, and that you will not use equations. Well, what's your take on that? Is it difficult to deal with publishers in
I happen to have had very good editors, and ones that I trust very much because were both very experienced editors. So whenever, you know, they would tell me, look, this is still too hard, I knew that I had to work more on that, you know, and do it. So I really trust they are very educated and very experienced. So I say, if it's hard for them, it's going to be hard for anybody. So I better work harder to try to make it, you know, more accessible.
Okay, we're going to come back to some of the specific ideas, as you mentioned group theory, in just a minute when we talk about the books. But I would like to add here for the audience that you provide a wealth of resources in all of your books. You can get plenty of additional information. It's first-rate information.
I write lots of notes and give lots of bibliography.
Yes, and in this, you'll see over and over again that he goes back to the original sources and investigates things very carefully, and it's just a very wonderful thing. Thank you for doing that.
Sure, yes. That's a lot of work. And I want to tell you, you know, maybe 2% of the readers actually go and read the notes and so on, but I feel that those 2%, you know, deserve to get that and get all that information.
Well, part of that is that when you read a lot of these books, you realize that we need to learn to be readers of a certain type. We can't read this sort of thing the way we read a novel, but we need to be a little bit analytical, and there is a huge amount of information. If somebody does provide the extra, it is much appreciated. That I started to say the percentage will go up. You wait.
I certainly hope so.
It will. Okay, now I want to go to your books, but all the books. But we'll start out with Brilliant Blunders, and I just heard last night that it made the New York Times bestseller list, and it's only been out a few months. So this is wonderful. We don't get a lot of science books on the bestseller list. Well, this is really a treasure. People have written books about mistakes that people make, but this is really special, and I would like you to give us an overview of the book, if you would, quickly, and I want to ask you about a couple of the unusual, less-known figures in it. Okay. So
basically, I wanted, first of all, to correct the impression that progress in science, or in fact any creative process, is a direct march to the truth. It is really not that at all. It is really the zigzag path with many, many blind alleys, false starts, you know, and so on, where you sometimes have to go back to the beginning and so on. And I wanted to convey that very, very clearly. And I decided to convey it through the works of 5 giant scientists, people like Charles Darwin, like Albert Einstein, to show that even these giant luminaries, they have made some serious blunders. And I concentrate on one blunder for each one of the people. Now, the 5 people that I discuss here are all connected also through a particular theme, which is the theme of evolution. This is evolution of life on Earth, evolution of the Earth itself, evolution of stars, and evolution of the universe as a whole. So these are the people I want. And indeed I wanted to give what I think is a more correct description of the progress of science, where blunders are part and parcel of what we do, and where this is the way that you make progress, in the sense, like, Karl Popper taught us, you cannot prove a scientific theory true, you can prove it false. And so what that means is that you progress with a particular theory until you hit a fact that does not conform, and then you have to change the theory. You cannot change the fact, and so on. So yeah, that's a very brief description of what's in this book.
It is very brief, but yeah, it will be surprising, I think, to people to know that people like Lord Kelvin or Fred Hoyle, as you have indicated, they may not be as particularly
well-known as Charles Darwin.
Exactly, but that could be stubborn, and like the rest of us. It's just a very nice thing to know that they're not perfect, and
they're humans at the end of the day.
They're very humans, and the book ends with a beautiful quote from Charles Darwin, who is delicious reading himself, if anybody has not tried him. But that it comes down to remember where you came from in evolution, that you came from very humble creatures, and it is a beautiful passage. It was a very nice way to end the book. But the book is full of that tone that we need to stay humble.
It's a call for humility.
Exactly, yes. Exactly. There are 4 more books that we're going to talk about briefly. The Accelerating Universe, because it's my favorite, and in that book, you are concerned with the term beauty. Beauty in science and beauty in aesthetics. Are they the same, or?
No, they are not the same, and in fact I was hesitant to even use the word beauty.
Everybody does.
Yeah, but people in the arts kind of stay away from that a little bit. What I was concerned with, I was trying to come up with, in my mind at least, with some sort of a definition of what is it that makes a theory of the universe beautiful. And I basically came up with 3 criteria that I thought, and I think most people would agree with those, even though maybe some will come with something a little bit different. So one was simplicity, in the sense of reductionism. You want to explain with one law as many as possible phenomena, not to have a different law for every phenomenon. The second was symmetry, indeed. And the laws of physics that we have are symmetrical. For example, they don't change from place to place, they don't change in which direction we look, and so on and so forth. And the third was this thing called the Copernican principle, which basically says that we humans are nothing special. I mean, the laws should be such that, they don't care about us so much, and so on. So, so I came up with a definition, and I tried to take that. I must tell you that, you say it's your favorite book. In some sense, it's my least favorable. No, only because of the following, because to a large extent, I've taken my day job there and wrote it as a popular book. And since I enjoy very much the research part, I actually liked the other books a little bit more, because I had to put more research into them than into the Accelerating Universe, which dealt with things that I deal with on a day-to-day basis.
Yes. But that book, I should emphasize, though, does deal with the nature of coming up with the equations and these ideas. And so if someone is not familiar with the idea of the simplicity or the symmetry and the Copernican principle, then this makes it very clear what science is about there. And it is full of art as well. So there's just references all over the place to art, and you're one of the very few who does this, and you have no problem with literature either. There are many references, especially I think more in this one, but can't remember. In any case, so the relationship between beauty in the sense, how do we recognize it, and I believe more than one scientist has said, well, I was sure I was right because the equation was beautiful. Is that true? Would you know it?
Yeah, Einstein, liked to say that a lot, that, the theory has to be right because it's so beautiful.
Exactly.
And so. Now, that's a little bit of an exaggeration because, of course, the theory, first of all, need to agree with all the observed facts, even before, you look at the beauty of it. But yes, we try for the theory to be beautiful in the sense that I described.
Right. Can you give us an idea of one that has been messy, of a theory that has been...
Well, it's not so much a messy, it's to understand what is the governing principle. For example, there is no question that general relativity, as written on paper, is more complicated than Newton's law of gravity. Yes, there is no question. It involves tensors and whatnot and so on. But the idea behind, the principle behind general relativity, that gravity is not some mysterious force that acts across space, but simply that bodies warp space around them, is in some sense simpler than Newton's idea, which didn't really give you an idea of how are these things affecting each other and so on. So in that sense, the idea is in some sense simpler, even though the appearance is much more complicated.
Okay. And I would just add to that, I don't know if this is the case, but it seems like inflation gives a fair number of headaches still. That it took a long... right,
it gives headaches, but at the same time, again, the idea was really simple. We had a whole bunch of perplexing observations, and then with this one idea, suddenly we solve all of them. So in that sense, it's very simple.
It is a good one then. Okay. Yeah. I'd like to go to the equation that couldn't be solved by, I think, the hardest, but extremely important, and that's, well, you tell us about that, but I want to make sure why group theory is so important too.
Group theory is the language of all the symmetries of the world. We are very familiar with symmetries of shapes or configurations. Our face has this, reflection symmetry and so on. But more importantly than these symmetries, or a snowflake you can rotate by 60 degrees and it remains the same. This is what symmetry means. You do something, but it remains the same. But the laws of nature have these built-in symmetries in them which are phenomenal. Like we have a symmetry where you can exchange this particle we call the electron with one you call a neutrino, and the laws look the same. The laws look the same for a person who is sitting, accelerating in a rocket, or sitting on a carousel. This is the essence of general relativity, and so on. So symmetries are really at the base of our universe. We would not have had these things we call laws of nature if our universe did not possess these kinds of symmetries. And then it turned out that one relatively simple mathematical language, namely group theory, explains all the symmetries, whether they are of laws, of music, of anything. This is this one language. And plus, there is an incredible story behind this, how this language was developed by this 20-year-old French mathematician who died at 20. I like to say, by age 20, what have I done? And I've done absolutely nothing. This guy invented group theory, before he died in a duel at age 20. This is amazing to me.
This is a really good story in the book about it.
So I decided I need to write that story.
With that you say that made clear a lot of things. Can you give us an idea of the sort of co-evolution between scientific developments like Einstein's relativity and certain areas of mathematics, that is, progressions in mathematics and like group theory.
Yeah, so for example, group theory, you know, when Évariste Galois, who was this French mathematician, when he formulated it because he wanted to test which algebraic equations can be solved by simple arithmetic operations and which cannot. That's why he did it. It had nothing to do.
He wasn't thinking science.
He wasn't thinking symmetry. He wasn't, you know, he did it for that. Well, it turns out that in today's particle physics, I mean, that's the language that everybody uses. They eat it for breakfast, you know. So suddenly, mathematical concepts developed sometimes with no application at all in mind. Decades or sometimes centuries later, some suddenly become the tools that are needed. And in Einstein's case, that's the same way. You know, Riemann developed certain geometries, again, just for pure mathematics. When Einstein developed general relativity, he discovered that's exactly the mathematics that describes the universe, you know, and so on. So yes, and this happens again and again.
But you're saying that they don't necessarily coincide, that the mathematicians think this stuff up, not necessarily, you know, from a phone call from
sometimes,
a physicist.
Sometimes they are connected, you know,
Yes.
like for example, Newton, when he wanted to describe motion and gravity and so on, he realized he did need some new branch of mathematics, and he developed calculus, you know, because of that. So yes, in that case it was connected, but sometimes it is not. And all of this, by the way, is the basis of my book, Is God a Mathematician?
Yes, and that's the next thing on the, so let's go to that then if we can. The little book, Is God a Mathematician? And I think one of the most frequent questions is, what's the God part of that? But tell us, if you will, the general outline.
So it's not a book about God, and not a book about the profession of God.
Yes.
Is God a mathematician is really put as a question in the sense that how come that mathematics has the powers that it has? How come that with mathematics we can explain the universe and so on? That's the question it deals with. And a related question, you know, whether mathematics is an invention of the human mind, or that it's somewhere in its own world and we are just discovering it, and so on. So that's the topic of that book.
And what is this is still a burning thing. I don't know if it's everybody's running around talking about it, but in the scientific community it comes up, I believe, and certainly there are philosophers for sure. But can you give us a good sense of that, whether it's Platonist, it's something out here and we sort of perceive it, or whether we make it up?
Yeah, my personal feeling is that it is a combination of both. That, you know, we invent some concepts and then we discover the relations among those concepts. That's what I think. But you know, there will be some mathematicians I will not convince of that. I mean, they still think it's somewhere out there and we just discover those truths.
So we still have this math phobia that we're dealing with, and we're trying to get rid of it. Growing up in Israel, did kids have this problem?
I think people have some problems with mathematics everywhere. I mean, you know, people, I don't know, like to talk about, I think Singapore is now leading, you know, the world in teaching mathematics and so on. It largely has to do with the level of teaching and things like this. You're not born with a fear of mathematics. I mean, at a certain point, you know, if your teacher is good, then, you know, you're not going to be fearful of this. Not everybody needs to be a mathematician.
True.
God forbid that everybody will be a mathematician. You know, people need to just have an appreciation of mathematics is all about, and how important it is for certain things, and that it is a part of human culture, in the same way that Shakespeare is. So in the same way that everybody appreciates Shakespeare, even though they don't necessarily become playwrights, everybody should appreciate mathematics, even if they don't become mathematicians.
Okay, and your books, as I said, particularly Golden Ratio, an equation that couldn't be solved, I think sort of push this, that people can understand this. And when you do, then even imperfectly, the world opens up, as you've tried to point out in many
arts. There is a new world that opens up.
Absolutely, and you're in a different place as for that. Now, I would imagine that Golden Ratio was probably one of the favorites, and you did a wonderful job, but you issued a warning in that book as well, I believe, about the golden numbers, I think it was called. But tell us what the book is about. And
so that whole book is about one number, which is 1.618, and it goes on forever like this. But this number shows some unexpected appearances in a number of natural phenomena, things ranging from arrangements of petals of flowers to quasi-crystals, for which Danny Schechtman got the Nobel Prize in Chemistry in 2011.
University there.
He was, yes, and so on. So it shows up in some phenomena. It also showed up in a variety of artworks, but not as many as people think, in the sense that lots of myths have developed around this number. At the end of the day, the number appears in some particular circumstances, either where there is a five-fold symmetry, or there is a particular algebraic equation that appears, all when one needs a very irrational number, one that cannot really expressed as the ratio of two integers, and so on. So yeah, I was somewhat surprised as to what an effect that book has had. I mean, that book really, lots of people reacted one way or another, and yes, I discovered that there are lots of people who sort of like to hang on to those myths, and it's hard to get them off that, even when you present evidence to the contrary.
Yes, and that's something, well, in your experience, but also you are very aware of our difficulty of giving up beliefs, ideas, prejudices that we've already got. You do a wonderful job with this. Let's go on to your passion for art. How many people have a passion for art in your field like you do?
Not that many.
Not that.
Not that many. Not that many. I mean, there are other people who like art, but I'm really quite passionate about this. Maybe it's because I have no talents in art, and so I appreciate it very much. So. And also, being a scientist, I cannot afford buying the real artwork, so I do the next best thing, which is buying books about art.
How many books?
I have many, probably in the thousands.
Of just the art
books about art.
Amazing, amazing.
But this is through my entire life, you know. I mean, the problem is, where do you keep all those books?
Exactly. Where do you keep all of those?
It's hard, I'll tell you. You know, I mean, the whole house is full of books. I can tell you that I have problems with my wife about that. Yes, but I like art and very much, and I like. You know, it's not that I like a particular branch of art. I mean, let me just say that I'm talking mostly about painting and sculpture.
Right.
I have a great appreciation for things like architecture and so on, but I don't see myself as at all as you know, being as passionate about that as that. So you have to concentrate on something. And even in the visual arts, I mean, I tend not to go that much into the ancient art, you know, not ancient Greece, ancient Egypt. I mean, I have some of that as well, but mostly it's, I would say, from just about pre-Renaissance, but up to the very modern art in both paintings and sculpture. Yeah.
In your books, where you refer often to artworks, it doesn't seem like, I was going to say, because it doesn't seem like, well, I'm stuck on the 19th century European or anything like this, or postmodern. They just pop up all over the place.
I write about something and I say, this reminds me of this Mondrian painting,
yes,
so I would write about it.
Right. So do you have a favorite period?
No, I don't have a favorite. You know, if really pushed to the corner,
pushing to the corner, right?
Well, and getting one favorite artist, I would say Vermeer. Vermeer would be my
that's
favorite.
the girl with the
girl
pearl.
with the pearl earring,
right,
but
right.
but not, you know, Vermeer. There are only 36 known paintings by Vermeer, but he was very much a theorist, as much as in the sense that, you know, every detail in his paintings he thought about really hard. You can see that.
Interesting.
Yeah. And this is why he also didn't paint very much, because you know, every painting is very thoughtful, and if he has a straight line here, then he will be sure to have something else that would break that straight line. You know, he has these colors, the way light falls in from the windows, and so on. I think he's an amazing painter. But at the same time, you know, I like, I don't know, Gerhard Richter, who paints today, you know, and so on. So, yeah.
It's very interesting. I wanted to labor that a little bit because of the dislike of science by many people in the arts. So, but there shouldn't be any disaffection there at all. This is really all one thing in many respects, and it's very helpful when you point out that a very famous artist went to great pains at analyzing everything, you know, to put things together, to make sure the
Plus there were even a few artists who were, you know, Piero della Francesca was a mathematician. I mean, he really knew mathematics. So there were a few artists who even really knew mathematics, and, you know, Dürer developed all these perspective things and so on. And, well, Escher was completely mathematical almost, yes.
Yeah.
So yeah.
But
now, of course, there weren't very many. There weren't very many like that.
Yeah.
Yeah. Leonardo da Vinci studied natural phenomena as well as you know, human emotion.
He was a brilliant scientist. In addition, he did just about everything.
Well, he just knew everything. Yeah. There aren't people like that anymore.
Okay. Is there, in closing, anything you would like to add that we haven't covered that you want to make sure we?
No, I would like, you know, young people to go into sciences, but I also would like them to love art, you know, at the same time. In particular, I want everybody to appreciate science as part of human culture. I mean, that if I have a message, and that would be my message, you know, like I said, not everybody needs to be a professional scientist. But everybody needs to understand that, you know, you look around you, and we couldn't do almost anything that we're doing now without science. Yes, I mean, I'm not even talking about things like the iPhone. I mean, you know, a smartphone today that has a GPS in it uses both Einstein's theory of special relativity and general relativity, because the GPS system needs to take care of the differences in the time because of these two theories. So you would not have thought that, you know, say, why do I need Einstein's special and general relativity? Well, guess what? The GPS system uses both. So science is all around us, and not everybody needs to design smartphones or things like this, but needs to understand that in the same way as we, you know, appreciate all kinds of other things, science is part of this, and we wouldn't have been here if not for all the science that we've done, and it has prolonged our lives by, you know, a factor of 2 over, you know, the last centuries, and so on. And in fact, you know, it's hard to predict advances in science, but I would not be surprised if within the next 100 years, aging gets slowed down by another factor of 2. You know, so it's amazing.
We need a new planet by that time, won't we?
So
one of those exoplanets.
If we won't destroy ourselves by some stupidity.
That is a possibility. Yes. And the other is perhaps you would endorse an attitude that is more scientific, that is the modern mentality would have to be more flexible, more open, more...
Flexible is a good point. I mean, I quote in Brilliant Blunders this quote from Bertrand Russell, who said that never be absolutely sure about anything. I think that's a good attitude. Yes,
it is a good. Dr. Livio, thank you very much for joining us today.
Thank you for having me.
I'll let you talk with people a little bit. We have to close down. Thank you.